right, folks, I want to jump into section 3 point, I think I called it, this is section 4.4 now, which is a summary of curve sketching. To be honest, there is no new material for this section. There's no new material in this section. Despite that, I think it's the hardest section we do in this class. The reason why is because you've got to, all the tools that we've been building this semester, plus some old ones from pre-calc and college algebra, come to apply to this section. Okay? I think I said this last time. Unfortunately, though, this is also the easiest MyMathLab section if you don't want to do the work. If you don't want to do the work, you just click multiple choice, click A, click A, click A, then it tells you what the right answer is, then you redo the problem, and then you know what graph to pick. Folks, on a test, you will not have multiple choice to figure out the graph. You will see questions like this. Here's a function, sketch it. That's what I'll tell you to do. Here's a function, you sketch it. Okay? So, here I've given you a list of steps that I think you should go through. When you're working the section 4.4 MyMathLab, please use these steps. Okay? I know that you can get through it without a lot of work, but I want you, that's a great chance for you to practice these steps. Okay? All right. So these three things are kind of straight out of college algebra. Find the domain of the function, find its x-intercepts, find its y-intercepts. Okay? The next one is symmetry. I don't use that one all that often, but if you know you've got an even function, or you know you've got an odd function, then you only have to evaluate half as many points. And you only have to sketch carefully half the curve, and then you can do symmetry arguments to sketch the other half. Okay, so it is a time saver, but if you miss the symmetry fact, that's not a big deal. So I'll highlight it in one of them, but it'll be the only time I do it. Then you do the vertical asymptotes and holes, and horizontal asymptotes and end behavior. To be honest, those are all things that you learned in college algebra, but now we've got the vocabulary of limits to discuss these things with, and I want you to use limits when discussing them. So if you're going to say there's a vertical asymptote there, tell me it's because the limit as x approaches the value is infinity, or minus infinity, or the appropriate left and right hand limits. Okay? All of these here are done by the chart that we did last time, or table, where you put up all your critical numbers of the first and second derivative, plus any places where the function's undefined, and you sketch for increasing this, decreasing this, concave up, concave down. Okay. If the function's bounded, then you've got to check your endpoints. That's something we've mentioned before. Okay, so that's that. And then you're ready to sketch the curve. Okay, so let's go ahead and do number 2 here. And let's see what we can do. First of all, let's identify the domain of this function. Well, in this case, identifying the domain isn't really all that exciting because it's a polynomial. So its domain goes from minus infinity to infinity. Okay. The next thing we want to do is we want to find the x-intercepts. To do that, we set f of x equal to 0. Folks, I need you to know that. To find x-intercepts, you set the output of the function to 0. You want the y value to be 0. That guarantees you're on the x-axis. Okay. Well, normally that's a chore, but I gave this to you in factored form, so it's not too much of a chore. Actually, it's no chore at all, since we have it in factored form. Folks, if I were to give you this problem on the test, I'd probably, well, no, I don't think I would have factored that for you. I don't think it's that hard to factor. But just to save some time in class, I guess I gave it to you in factored form. Okay? But sometimes I might give you the first and second derivative if I think that those would take a long time to calculate and then simplify, or I might evaluate a couple points for you, stuff like that. Okay? All right, so let's see here. We have x-intercepts when x equals 0, when x equals minus 4, and when x equals minus 3. Now let's go ahead and find any y-intercepts. we've actually already done the work for the y-intercepts. We've got a y-intercept of the order pair 0, 0. Okay? But again, how do you find y-intercepts? By evaluating the function at 0. By plugging a 0 into the function. Okay, so hopefully you know the difference between x-intercepts and y-intercepts, between finding those. Okay, we're running through the list. We're doing pretty good. Does this function have any symmetry to it? No, it's neither even nor, no, it's neither, I don't know. Let's think here just a second. Negative x, no, it's neither even nor odd. This one? What's that? That's a good question. If you don't know from just looking at it, don't worry about it. Okay? There'll be another one that I'll point out to you. What I did here was I plugged in the number negative x and see what I got, see if how it's simplified. When I plug in a negative x, this term would just have a negative in front of it. This term would just have a negative in front of it, but this term would not. So I can't factor a negative out of all three of them, so it's not odd. And it doesn't absorb all the negatives either, so it's not even. Yeah, that's the easiest answer I can give for the moment. Okay, so we checked, and again, this is not one that you usually have to do. Okay, this is one that you seldom need this. All right. Now what? We want to go looking for vertical asymptotes and holes. What say you to that question? Where are the vertical asymptotes and holes of this function? Where are the vertical asymptotes and holes to this function? Yeah, there aren't any. How come? Ah, I think that's probably the ideal answer, right? We said vertical asymptotes and holes arise from what? Exclusions in the domain. What number was excluded from this domain? None of them. So you can't have any vertical asymptotes or holes. None. Sometimes that'll happen in these questions. Okay. 5, let's look at for horizontal asymptotes and long-term behavior. Okay. How do we look for horizontal asymptotes? Yeah, I agree with y'all. We say we look at the limit as x approaches infinity of our function. Okay, I'm going to go ahead and write it out. Could somebody read it to me? It was x cubed, x to the 5th, I mean? Plus, okay?
Plus 12x cubed.
Is that it?
Yeah.
Okay. So, oh, this one's actually really easy to analyze. Notice this is becoming arbitrarily large, arbitrarily large, arbitrarily large, and I'm summing them up. Okay, so since I'm just summing them up, I can go ahead and say that limit will be infinity. Okay. Now for this next one, the limit as x approaches, to check for asymptotes the other way, we got to look at the limit as x approaches negative infinity, right? Well, for this one, what is the indeterminate form here? Yeah, or this will be minus infinity, this will be plus infinity minus infinity. That's an indeterminate form, right? So maybe you're by the way, you're welcome to use your college algebra skills on this one if you remember what this limit is. But what did we say to do? Well, try to maybe write it as a product. I think if you go back to the notes for indeterminate forms or indeterminate difference, I said one thing you could do is factor out common factors. If we put this into factored form, we've got the limit as x approaches minus infinity of, what was this? X to the 3rd times x plus 3. Now, that's arbitrarily large negative times arbitrarily large negative times arbitrarily large negative. Okay. The next part, so we've gone through that. Check, check, check. Now we're going to do the chart. right? We said the rest of this information we can get from the chart. What goes on the chart? On the chart goes any exclusions in the domain, and then critical numbers from your first and second derivative, which are critical numbers from the function and the first derivative, which are your potential locations for local maxes and mins, as well as your potential locations for
Local.
this one says, no. Inflection points, right? Okay. So, to be able to determine that, we better find the derivative. So f prime of x is equal to 5x to the fourth plus 28x cubed plus 36x squared, which gives us x squared times 5x and x and 2 and 18, I think is good. So that gives us 2 and 18 and plus and plus. Okay. So I believe then that the critical numbers of f are x equals 0, negative 18 fifths, and negative 2. Any questions on that? Okay, now let's go find the second derivative. The second derivative is 20x cubed. Oh, good golly. 20x cubed plus, let's see here, 90 minus 6 would be 84. X squared plus 72x, I think. Oof, golly. Let's see here. We get a 4 out of all those? Yes, yes, yes. So let's get 4 out, 4x. That leaves us with 5x squared plus 21x plus 18, I think. I would probably give you these derivatives in factored form, because this one's this is taking a little too long. But it's fine to do in class. Okay. So let's see here, this would be 4x times 5x and x. And let's see here, we got 18, and I think we could probably do, let's see here, we gotta get to 21. Oh, what's that?
6 and 3.
Yeah, thank you. 3, 15, and 6, good, and plus and plus. Okay, so it looks like we've got critical numbers of f prime, and they are x equals 0, negative 6 fifths, and negative 3. Yeah, so this isn't, I'm not gonna try and trip you up with this naming issue, okay, but I do need to distinguish between the two critical number sets. These are my potential locations for local maxes and mins. These are my potential locations for inflection points, okay? So I do want to distinguish between the two, and their appropriate names are this. To find the critical numbers of a function, you look at that function's derivative, or where that function's derivative is undefined. So to find the critical numbers of f, I looked at f prime. To find the critical numbers of f prime, then I look at f double prime. Okay, I'm not going to try and trip you up with that, but I do need to distinguish between those, because we want to talk about possible locations of maxes and mins versus possible locations of inflection points. Okay, we are ready to go. I'm going to do this on another page. So we build ourselves a number line, and on the number line we put all of our interesting values. Those include any place where the function's undefined, and anywhere where the derivative is either 0 or undefined, or where the second derivative is 0 or undefined. Excuse me. So help me out. Let's see here. What was our leftmost critical number? Yeah, negative 18 fifths, then negative 3, negative 6 fifths, negative 6 fifths, and then what else do we get here? We had 0, 0, oh we have negative, are they all negative? Ugh, that's ugly. Yep. So shoot, this one would be negative 2. This is negative 6 fifths, and then 0. Okay. Okay, so now we need some test points. Okay. Let's call this one, let's see here. So let's just do this at negative 4. Let's see here. Let's do negative 3.2. Let's do this at negative 2.5. Let's do this one at negative 1.5. Let's do this one at negative 1 and this one at 1. So we look at our derivative, and we're going to plug in the test points into the derivative. So that's positive 18 fifths and 2. So this is negative and negative, so we're increasing. Then we are decreasing, decreasing. When we plug in negative 2 or negative 1.5. Sorry, I can't do this in my head. That's positive, positive. Everything's positive from beyond there. So we're increasing, increasing, increasing. Okay. Double check me on those folks because I'm jumping back and forth between 2 pages there. Okay, so those were f prime of the test point. And then we'll look at f double prime of the test point. So let's see, we plug these into the second derivative. Besides the sign, 6 fifths and 3. So it's negative, negative, negative. So I think we are concave down, concave down, concave up, concave up, concave down, concave, concave up. Folks, if you check me on that, because I don't have the function in front of me to plug these values into, so I did them all in. All right, so let's just identify what we've noticed. We have just identified that we have some local maxes. Where are our local maxes? We have a local max where? At x equals negative 18 fifths, right? And we found that we have a local min where? At x equals negative 2. What else have we found? We found some inflection points. We have an inflection point at x equals negative 3, at x equals negative, is it 6 fifths? And at 0. 3 inflection points. Okay? Okay. All right, now we got kind of a difficult task. We now need to evaluate all these. We need to find actually all these ordered pairs. Okay? So, if I could have these 2 tables here, if you would plug in negative 18 fifths into the original function, it's going to be fastest if you plug it into it in factored form, right? So plug negative 18 fifths into the original function. If these 2 tables here, if you would do negative 6 fifths into the original function, and this table here, if you would do negative 3, and this table here, if you do negative 2, okay? negative 8.71 for this one. Okay, I'm just going to put approximates on there. I'm not worried about this right now. Okay. Anybody else? This is negative 16. Folks with negative 18 fifths, what'd you get? 11.2? Great. We'll just call it, I'm just going for the approximations right now, folks. All right, now we're ready to graph this thing. Okay. So, we said that we had zeros where? At x equals 0, at x equals, what's that?
-3.
Okay, at x equals -3, and at x equals -4. Right? Those are our zeros to the function. Okay. Then we said we had a y-intercept, but where was our y-intercept?
0, 0.
At the origin, 0, 0, so we've already got it. Okay, great. Then we said we had no vertical asymptotes or holes, so there's none of those to put on. Then we said as you go far to the right, your y value should become positive. And as you go far to the left, your y value should be negative. That's the end behavior, right? That's our end behavior. Okay. Okay. Then what? Well, we said we had local max at the ordered pair negative 18 fifths, comma 11.2. So that's, I don't know, negative 18 fifths was maybe right about here. Okay, so let's call that about 11.2. If you want to wait on labeling your points till after you've graphed it so you don't get your label in the way of where you're going to draw your lines, that's probably a good idea. Okay. Then we had a local min at -2 comma -16. So where's that? That's down here. Okay. Then we had 3 inflection points, one at 0, 0, one at -3, 0, and one at -6 fifths, comma -8.75. So one about here. Any questions about that, folks? Tough stuff. Tough stuff. We're ready to put it all together. From minus infinity until I get to negative 18 fifths, what am I doing? The function is increasing in a concave down manner. Show me concave down. Where on that would you be increasing? So your graph should look like that. Okay. So here we are. Until we get to this point right here, we're going to be increasing in a concave down manner. So there we go. We're increasing in a concave down manner. Then, from negative 18 fifths until we get to -3, I'm talking about this interval right here. On this interval right here, what am I doing? I'm decreasing now, also in a concave down manner. Show me decreasing, show me concave down. Yeah, we are decreasing in a concave down manner until we get to there. Okay. At -3, we've got an inflection point. At the order pair -3, 0, we've got an inflection point. Now we will continue beyond, once we leave -3, we're going to continue decreasing, but now in a concave up manner. Concave up, decreasing. So we're decreasing in a concave up manner. Until we get to x equals -2, at which point we've got our horizontal tangent line. And then we start increasing, still in a concave up manner. And then at that inflection point, we're now increasing in a concave down manner. And then we again continue increasing in a concave up manner. Okay? All right. There's the graph of this function. I think that's fairly impressive how accurate we're able to be with this. Okay? I do want to claim, I do want to say a couple things that I'm not going to really hold you accountable for, but I just want to say that it's there. This point was both a place where I had a horizontal tangent line and an inflection point, right? So what should be the slope of the tangent line there? It should be 0, so it should level off there completely. Okay? I've also sort of got an error. If I were doing this on a test, again, I'm not going to hold you responsible for it, but if I were doing this, I might kind of come through and fix this, because I don't quite want to be going through it at a, I don't want to quite be going through it at a vertical, because if it were dead vertical the way it looked there, the first derivative wouldn't have been defined there, right? Vertical tangent lines are undefined, and that wasn't the case. Okay, so there's a couple things you could fix slightly with that, but essentially we've graphed this polynomial function, a fairly complicated polynomial function. Okay. Specifically in college algebra, you were never able to find, where to put your peaks, and if you had some sort of interesting inflection point other than at the origin, or on the x-axis, you had no idea where to put that. All right, so let's go ahead and do number 3 here. Okay. Notice that for number 3, if this were a test question, I feel like finding the first and second derivative can be time consuming. Specifically, putting the second derivative into factored form can take a lot of time. So I went ahead and did that for you. Okay. All right, let's graph this thing. Okay. What's the first step? Look for the domain. What's the domain? X can be any real number except for what? 1 and -1. Everyone okay with that? You can write this, you can use interval notation, you can use set builder notation. I don't care which one. Now folks, when I go to build my chart, even though -1 and 1 can't be critical numbers, I do need to remember to put them on my chart. Because on either side of -1 and 1, I can change from increasing, decreasing, I can change concave up, concave down, who knows? So I've got to check those. Okay. Then what do I look for? The x-intercepts, the zeros of a function. So how do I do that? Set f of x equal to 0. You set the output to be 0. That happens when this fraction is 0. But when is a fraction 0? When the numerator is 0. And when is this numerator 0? When x equals 0. So x equals 0 is an x-intercept. At that point, we already know then what the y-intercept is. The y-intercept is the ordered pair 0, 0. Any questions on that? Okay, what do we look for next? Yeah, let's look for vertical asymptotes or holes. Where should we go exploring? We've got this powerful tool, this limit tool, allows us to look at things. Where should we shine our light on? We should look at 1 and -1. Those were the two exclusions in the domain. So there are potential locations for vertical asymptotes and holes. Okay. So let's look at the limit. As x approaches, let's do 1 from the right of our function, which is 2x squared over x plus 1 times x minus 1. Okay. These tools require us to go way back to chapter 2. Remember that one test question that had the rational function? It's kind of, it's usually the most disliked question on that first exam. The numerator is approaching what? 2. This factor is approaching a small a positive number, and this is approaching a very, very small, but careful, we're approaching 1 from the right, so we're not numbers like 1. So this is approaching positive infinity. Everyone okay with that? Luckily, we just got to review that on our midterm, right? We did problems like this on our midterm. Okay. let's look at the limit as x approaches 1 from the left. That'll be negative infinity. Okay? Either one of these two facts is enough to say that we have a what? A vertical asymptote at x equals 1. Now let's look at the limit as x approaches negative 1 from the right. Okay. We're plugging in numbers to the right of negative 1 like what? Be careful with this one. Negative 0.9. So this expression right here is going to be very, very small but positive. That comes out to be positive infinity. Then if we look at the limit as x approaches negative 1 from the left of f of x, that comes out to be negative infinity. Okay? These two facts tell us that we have a vertical asymptote at x equals negative 1. Okay? All right, folks. I want you to give me these limit statements. Okay? Now, so if I ask you for vertical asymptotes and holes, I want you to give me these limit statements. Now, in college algebra, you said, oh, these factors aren't going to reduce out, so I know I've got vertical asymptotes at 1 and negative 1. So you already knew that before we went looking and explored the limits. If you wish to graph this and then make these limit statements, fine, I can't stop you from doing that. Okay? But notice that the limit statements actually help me with the graphing. Okay? At this point, we could jump to the graph part. There's our vertical asymptotes. And we said as we approached negative 1 from the left, we were approaching negative infinity. And as we were approaching negative 1 from the right, we were approaching positive infinity. And as we approached, I'll double check that. Folks, we made a mistake here, didn't we? Yeah, hold on. Hold on. Hold on, hold on, hold on. This is approaching very, very, this is a small positive, but this already had a negative factor here, right? Because this is negative 2 minus, or negative 1 minus 1. So this was approaching minus infinity. This was approaching positive infinity.
Isn't the top negative as well? Oh,
No, because of the squared there. Yeah. Folks, did you catch that? That should have been negative infinity over positive infinity. Did you guys catch that before? Check me. Sometimes I purposely make mistakes. No. I mean, sometimes I do, but not there. Okay. But you should be checking me as we go through these. All right. All right, so anyway, we said as we approach negative 1 from the left, we're approaching positive infinity. That gives us that. And as we approach negative 1 from the right, we're approaching negative infinity. And as we were approaching 1 from the left, we were approaching negative infinity. And as we were approaching 1 from the right, we were approaching positive infinity. Okay. Any questions? So you see why, I mean, doing these limits helps you significantly with the graphing. Okay. But for one of these problems, yeah, you knew what the vertical asymptotes were before you learned calculus. So if you want to do it that way, that's fine. But you do need to make your limit statements. Okay. So I do want to see those limit statements. Okay, so that was vertical asymptotes and holes. Who's next? The horizontal asymptotes slash end behavior, right? Okay. So Avery, what am I going to do for the for the end behavior?
Limit as x approaches positive and negative.
Yeah, we're going to look at the limit as x approaches infinity of 2x squared all over x plus 1, x minus 1. Oops, let's leave it as x squared minus 1. And what is that? What is that limit, Darcy? What's that limit going to be? Yeah. So you can you're welcome to use your college algebra skills to say, hey, the degree of the numerator is the same as the degree of the denominator. So you can look at the ratio of the leading coefficients. The more sophisticated way is the way we taught in, I don't know, section 2.5, where we said multiply by 1 over x raised to the highest exponent seen in the denominator. At some point you would have then a 2 plus a 0 over a 1 minus 0, and that's how you'd get 2. Of course, we now have one new tool, right? What else could we do for graphing this? This has indeterminate form, infinity over infinity. So we could apply L'Hopital's rule, but we'd have to do it how many times? Twice. And if we did it twice, we'd end up with a 2 as well. Any questions on that? Great. So that's horizontal asymptotes and behavior. Okay. Normally, we'd have to now compute the derivatives. I went ahead and did that for you and put it into factored form. That was awfully nice. So now that we've done that, we can identify the critical numbers of f. What are the critical numbers of f? They are where f's derivative is 0 or undefined. Where is f's derivative 0? At x equals 0? Where is f's derivative undefined? It's undefined at 1 and negative 1. Are those critical numbers? No. Jillian, you're shaking your head. Why not?
Because they're restricted in the domain, right?
They already weren't in the domain to begin with, right? To be a critical number, you've got to be an interior point of the domain, and then where the derivative is undefined. Okay? So even though something interesting is happening at negative 1 and 1, we're not going to call them critical numbers. Okay, let's look for the critical numbers of f prime. Max, how do I find the critical numbers of f prime?
Isn't it in the first derivative, the ones that equal?
So careful. This is a tough point. For the critical numbers of f prime, I'm going to ask where is f prime's derivative? 0 or undefined. So what am I actually looking at here? So to identify the critical numbers of a function, whatever it is, you look at its derivative. Yeah. So to identify the critical numbers of f prime, I'm going to look at what?
What equals 0 derivative, or not equals 0.
I'm going to look before I do. I'm going to look at the second derivative, right?
Yeah.
So when I'm looking for the critical numbers of f prime, I'm looking at this second derivative here, right? Okay. So where is it undefined? At 1 and negative 1. But I'm not going to include those because they were already excluded in the domain. So what else could happen? The second derivative could be 0. When would that happen? Well, that would happen when 3x squared plus 1 equals 0, right? But that happens when 3x squared equals negative 1 or when x squared equals negative 1/3. Does that ever happen? No, because you can't, I mean, if you square a number, you can't get a negative. Okay, so there are no solution. So there are no critical numbers of f prime. Okay? So, in terms of what we said, remember I said the critical numbers of f give us potential locations for local maxes and mins. So we've potentially got a local max at x equals 0. Or a local min, excuse me, we've got potentially a local extrema at x equals 0. We got to go explore it. What did the critical numbers of f prime give us? What do you say, Veronica?
We look for the concavity.
So the second derivative tells us the concavity, and so the critical numbers of f prime will tell us potential what points?
Inflection points.
Inflection points. So in fact, we can go ahead and say that this function has no inflection points. Careful, I'm not saying it's not ever going to change concavity, but it's never going to change concavity at a point where the function's defined. Does that make sense? So it might change concavity somehow, but not at a place. You won't be able to point to where it changes concavity, at a point on the graph. Okay, so what do we do next? What do you say, Daniel?
Draw a line,
We draw a number line.
test points.
What's going to go on this number line? What's one thing that's going to go up there? What do you say, Daniel?
The 1 and -1.
The 1 and -1, okay? So let's go ahead and put -1 up here. Let's go ahead. And why am I putting those up there?
Because we know those are like points where it doesn't exist or it's 0.
Well, which is it?
In this case, it doesn't exist.
Yeah, so this is where f is undefined. Okay, that's really helpful because if I change from increasing to decreasing there, am I going to call it a local max? No, because it's not defined there. Yeah, there's no actual there's no actual point there on the graph. Okay, great. So what else is going to go up there, Journey?
Find f prime, or you put the numbers in between.
Well, before I do that, before I do my test points, I don't think I put all the ordered pairs up, or all the values up on the number line. I got to put one more up there.
X is equal to 0.
Exactly. And why is 0 going up there?
It's an x-intercept.
It is an x-intercept, that's true, but we don't necessarily have to put the x-intercepts on the graph. Or on this number line, I mean.
Is it equal to 0?
What is?
The function.
No. So yeah, so let's go over what goes on this number line, because this has been what goes on the number line has continued to kind of change as we've gone through these last couple sections. So on the number line, when you're graphing a function, you're going to put all the places where the function's undefined, all the values if there are specific values. Then you're going to put all the critical numbers of f and all the critical numbers of f prime. So I agree that we're going to put 0 up here, but how come?
It's a critical number of f.
It's a critical number of f. Specifically, it was where f's derivative was 0. Okay. All right. Good job. Oops, too far. All right, folks. So now I'm going to go ahead and make my pens. And as Journey said, we're now going to pick our whats? Test points. So how about, I don't know, -2, -0.5, 0.5, and 2. Then we're going to look at f prime of the test points. Okay. So let's see here. We've got this first derivative already in factored form. Notice that the denominator will always be positive. And so we get that we start off decreasing. Is that true? I feel like that's not true. Let me double check that. The denominator is always going to be positive. We plug in a -2 for x. We get that this is positive, so we're going to be what? Increasing there. Okay. When we plug in -1/2, will be the same. We'll be increasing. When we plug in 1/2, we'll be decreasing. When we plug in 2, we'll be decreasing. Okay. Now let's look at f double prime of the test point. So now I'm plugging the test points into the second derivative to determine their whats. What am I determining here? Concavity. So plug -2 into the second derivative. Notice that the numerator will always be positive. So the only sign is the negative. But -2 squared is 4. 4 minus 1 is positive when I cube it. So we are concave up. But if I plug in -1/2 or 1/2, I get concave down. And if I plug in 2, I'm back to being concave up. Okay, so I'll let you check me on those. I did those kind of fast. All right, did we notice anything? Did we find any points of interest? So Curtis, what have I got up here? What's one thing that we found?
Changes concavity twice.
So it did change concavity twice, right? So did that give me inflection points?
Not necessarily. That's where it's not defined.
Yeah, so even though, so yeah, I think it's good to note that we changed from concave up to concave down at x equals -1. But why was -1 up there? Because it's where the function was undefined. So is that an inflection point at -1? No. All right. So there are actually, so we have some changes in concavity, as Curtis said, but we have no inflection points. Okay, what else is interesting up here? What do you say, Max?
Sorry, I was zoning out.
Yeah, that's okay. We're looking at our chart here. Before I go to graph, I mean, we're looking for inflection points, local maxes, local mins. Did we find anything?
Or -1/2 and 1/2 both. I mean, both concave down.
Yeah. And so on this interval from -1 to 0, we're concave down. Good. And from 0 to 1, we're concave down. Okay. So what else are we looking for? So we already ruled out that there are no inflection points. So why are we building this chart? This chart's going to help us find intervals for which we're concave up, concave down, intervals for which we're increasing, decreasing, but it's also going to enable us to find inflection points by looking at where it changes concavity, and it's going to enable us to find local maxes and local mins. So what do we see up here? Is there anything else we see? Try it one more time.
I mean, the negatives are increasing and the positives are decreasing.
Yeah. So remember from this chart, we can determine where we have local maxes and local mins if we look at the first derivative. Okay? So what were we doing before we got to 0? What was the function doing before we got to 0 in terms of the first derivative?
It was increasing.
Increasing. And after we left 0, what's happening?
It's decreasing.
And why is 0 up there? Because it's a point on the function where we had a horizontal tangent line. So what did we just show? At x equals 0, we've got a what?
A whole.
No. So our derivative changed from positive to negative. Okay. So even look at the picture that we kind of drew. What's that?
A local max.
We've got a local max. Exactly. Exactly. So at x equals 0, we have a local max. Great. Okay. Folks, these graphs take a long, long time for me to talk through in class. Okay. You want to be able to graph these graphs in about 10 minutes. Okay. You don't want to spend, on the next exam, you don't want to have to spend 45 minutes graphing these. So you do want to practice going quickly through these. Okay. You have to practice a lot of them to be able to do them quickly. All right. We're ready to now put this all together. Okay. So I go through, I put up any x-intercepts. Oh, we said we had an x-intercept at 0, 0. Then we go and we put up any y-intercepts. Oh, we said we had a y-intercept at 0, 0. I put up any vertical asymptotes or holes. Did so. Horizontal asymptotes. Oops, did we remember to do that? We did, yes. And we said we had a horizontal asymptote where? Y equals 2. There's our horizontal asymptote. Okay. So putting all, oh, and then we go ahead and put up any local maxes and local mins. Well, we've got a local max at 0, 0. And then we go ahead and we put up any local mins. We have none. And then we go ahead and put up any inflection points. We have none. Okay. So now we're ready to put this all together, and it's the chart that gives us the missing bit of information. Okay. We know that initially we're going to start off, until we get to x equals -1, we're going to start off increasing in a concave up manner. Show me concave up. Show me increasing on it. Okay. So what's the graph doing? It's behaving like this. How do I know I don't have any fluctuations in there? Because it would give me local maxes and mins that I would pick up on, or inflection points that I'd pick up on. Okay. Okay. Then I said sort of whenever you get to a vertical asymptote, it's kind of like you've broken the graph into segments. So time out, start over. Okay. As I leave the vertical asymptote, I am increasing in a concave down manner. I arrive at my local maximum at 0, 0, and then I continue decreasing. Now I continue decreasing, still in that concave down manner. We get to the next vertical asymptote, we start over, and we're decreasing in a concave up manner. Did this graph change concavity? Oh yeah. Do we have any inflection points? No, there's no place where it changed concavity. Questions on that, folks? Comments?
So, critical numbers, that determines if you have local maximums.
So let's be careful. The critical numbers of f, which are where f's derivative is either 0 or undefined. Okay, so the critical numbers of f give you potential locations for local maxes and local mins. Exactly. The critical numbers of f prime, which are where f double prime is 0 or undefined, give you potential inflection points.
They has to be where it's defined, right?
It's got to be where the original function was defined, actually where even f prime was defined. Yeah. So, one way to say it is the critical numbers of f and f prime give you potential locations for local maxes and mins and inflection points. But I've been trying to distinguish between the two. Okay? Because if we saw here, because we had no critical numbers of f prime, we have no potential inflection points. But we did have critical numbers of f, so we did have a potential max or min, and we discovered it was a local max, basically using the first derivative test. Great question. Okay, number 4. Okay. Oh, by the way, number 3, you guys sketched graphs like number 3 in college algebra, you remember? Okay, so I like to make sure that you always get a question on this exam that involves a curve that you couldn't sketch in college algebra. Okay? We've seen one already, e to the 1 over x. That was a graph you could not sketch in college algebra. Here's another one. Okay? F of x equals x e to the x. Okay? All right. Let's run through it. What's my domain? What's the domain of this function? All real numbers, exactly. All real numbers, good. 2, what do we do in 2? We look for our whats? What are we looking for, Jillian?
X-intercepts?
X-intercepts. How do I do that? Maybe we can take that one. How do I find x-intercepts? What's that? Exactly. Everyone hear what George said? Set f of x equal to 0. I don't think anyone should come out of college algebra without being able to know, okay, to find x-intercepts, you set the function equal to 0. To find y-intercepts, you evaluate the function at 0. Okay? All right, so we set it equal to 0. That happens when x e to the x equals 0. That happens when either x equals 0 or e to the x equals 0, using the zero product property. When is e to the x equal to 0? Never, right? E to the x never outputs a 0. Okay. How about this one? Well, x is 0 and x is 0. Okay, so we found an x-intercept of 0, 0. Now what do we find? Kevin, what do we look for next?
The y-intercept.
Okay, and we've already answered that question, right? Because to find a y-intercept, we evaluate the function at 0, but that's just 0. So what's the y-intercept? 0, 0. Alrighty, so that's our y-intercept. Now what do we look for? Let's look for, let's go ahead and do vertical asymptotes / holes, because we can knock that one out real fast. Where are vertical asymptotes and holes? What do you say, Brandy?
When the limit approaches,
So how do we find vertical asymptotes and holes? We look for
the
So this is definitely a phrase worthy of a flashcard, right? So vertical asymptotes and holes. arise from the exclusions in the domain. Right?
There's none.
Ah, what's that?
But there's none.
But there's not any. So where are vertical asymptotes and holes? There are none. Does that make sense, everyone? To have a vertical asymptote, the function can't be defined there. To have a hole, the function can't be defined. Well, that's not quite true. It would also be like if it's a piecewise function, a boundary or something like that. So I should be a little more careful there. But you still have an exclusion in the domain when you have a hole somehow in one of the pieces. Okay? All right. So now what should we look for? What do you say, Logan?
Horizontal asymptote?
Horizontal asymptotes or / in behavior, right?
Yep.
I.e., is it approaching infinity or minus infinity or 3 or something? Okay, how do we identify the horizontal asymptotes? What do you say, Avery?
As the limit as x approaches positive or negative.
Right, in behavior, that's far to the right, that's far to the left. So our x values are going to approach infinity. Okay? All right, first one, as we approach infinity, that's straightforward. What is that limit? Everyone write down what you think that limit is. Curtis, what do we say that limit is? What's that? It is just infinity, right? Because each factor is becoming arbitrarily large, and the product of two arbitrarily large numbers is arbitrarily large. Is that an indeterminate form? No, think about that word, indeterminate. No, we can claim with all certainty what that's going to be. Okay? All right. Now let's look at the limit as x approaches negative infinity of x e to the x. What's that limit going to come out to be, folks?
Negative infinity.
Is it? Why do you say that, Daniel?
Well, you have the x, which is being multiplied, so you have negative infinity,
Okay.
and then you have e to the, which would also be the negative infinity.
Is it? So what does e to the x look like? There's the graph of e to the x, right? So as I go far to the left, what are my y values doing?
Approaching 0.
Ah, they're approaching 0. So is this the indeterminate? So it's a good question. Is this the indeterminate form negative infinity times negative infinity? No.
No.
What is it? It's indeterminate form what times what?
Negative infinity times 0.
Ah, and can I evaluate that? Can I just say, oh, I think I know what that's? It's going to be 0. It's going to be negative infinity. It's going to be 12. Can I say with any? No. Because this is an example of one of our indeterminate forms. Specifically, we call this an indeterminate product. So now I've got to evaluate this limit. This is not an easy one. So what am I going to want to try to use to evaluate this limit? Any guesses on that?
I'll rewrite it with,
Go ahead.
because we do want to get 0 over 0 or infinity over infinity, but we need a quotient.
Okay, so our goal. Okay, so once Daniel identified this is the indeterminate form minus infinity times 0. Our goal is to try to evaluate this. We're probably going to have to use L'Hopital's rule, because we usually have to use L'Hopital's rule when we have the transcendental functions like e to the x, natural log of x, sine of x. Those are functions that are harder to work with, okay, harder to do limits with. So I think I'm going to want to use L'Hopital's rule, as Zach and Daniel said. But Kevin said, wait a minute, we can't use L'Hopital's rule yet, because L'Hopital's rule requires it to be 0 over 0 or infinity over infinity. So what am I going to do? We're going to rewrite this somehow. What did we say to do? So this is going back to our material from last time, from Thursday. We take one of these two factors below the line and we invert it. Okay? Which one would you like to take below the line and invert?
X.
Oh, interesting. Okay, let's do it. So this would give us e to the x divided by 1 over x. So now we apply L'Hopital's rule, and what do we get? We get the limit as x approaches negative infinity of e to the x over minus 1 over x squared. Which gives us indeterminate form 0 over 0. We apply L'Hopital's rule again. We get the limit as x approaches minus infinity, don't keep writing, of e to the x over 2 times, let's see, of 2 over x cubed. We getting anywhere, folks? No, we're not getting anywhere. So at some point we made a choice. Okay, not a bad choice. I mean, that was the choice when we were working with logarithms. You said take the x down below. Okay. What do you think? What should we do?
EDX then.
Yeah, so let's backtrack, and instead of taking x below the line and inverting it, let's take e to the x below the line and invert it. So we're going to have x over e to the minus x. Right? When you invert e to the x, you just get e to the opposite power. Hey folks, those of you that suggested that we take the x down, thank you for suggesting it. It was dead wrong, but thank you for suggesting it, because that's what you do. You try it, and if things get more complicated, then you go back and you take the other expression down below. Okay? There's absolutely nothing wrong with taking a swing at that one, because I don't think it's always clear which one you should take down below the line. Okay? So just do it, and then find out whether you can work with it or not. Okay? But it turned out it was easier to take e to the x down below the line. Okay? So now this has indeterminate form, what? Negative infinity over infinity, right? Because this x is approaching a large negative number, e to a minus, yep, okay. So we get, through L'Hopital's rule, remember I want you to put LH when you apply L'Hopital's rule, so that I know, that you know, that we all know what's going on. Okay. So we then get the limit, as x is still approaching negative infinity, of 1 over minus e to the minus x. Which is equal to the limit, if you can't evaluate that off the top of your head, no worries. The limit as x approaches negative infinity of minus e to the x when I bring everything back up above the line. Hard time seeing that. Okay? And what is that limit? What do you say, Darcy? It is. It's 0. Okay. Let's see here. I think we're on track. We did the domain. We found the x-intercepts. We found the y-intercepts. We looked for vertical asymptotes and holes. There were none. We did the horizontal asymptotes just now. And we found, oh, there's no horizontal asymptote as we went to the right. This function is just going to take off as we go to the right. But as we go to the left, this e to the x is going to, as we plug in large negative numbers for x, this e to the x is going to drag us to 0. Yeah, George, there's a question.
No, I understand it now.
Oh, good, good. All right. Any questions on that? All right. So now what do? Now we use our derivatives for increasing, decreasing concavity, right? So let's go ahead and take some derivatives here. F prime of x is equal to the first times the derivative of the second plus the second times the derivative of the first, which factors to be x plus 1 e to the x. You remember taking this guy's derivative a couple times? We did it right after we introduced the product rule. Okay. What are the critical numbers of f? They are where f's derivative is either 0 or undefined. Well, this derivative right here is never undefined, but it is 0 when x equals -1. So as Thomas said last time, -1 is a potential location for a what or a what?
Min or max.
Yeah, let's say local min or local max. Okay. Now let's go ahead and find the second derivative. Okay. I'll let you check me, but we've done this one a few times, so I know it's second derivative. You wouldn't get there right away. You'd have to FOIL it out and then combine and factor. Okay. So what are the critical numbers of f prime? X equals -2. What are we saying there? We potentially have a what at x equals -2? Inflection point. Okay. Getting to my favorite part of this game. Veronica, what do we do now?
The number line, put the critical numbers on.
Yeah, so we're going to make a number line. On the number line, we're going to put our critical numbers. We found that -2 would be the leftmost one. -2 was a critical number. Why? Because it was where f double prime of x was 0. -1 also because it's where f prime of x equals 0. Okay. And what else would we potentially put up on this number line? We're not going to do it in this case, but what else do we normally put up on this number line? What do you say, Journey?
Where would be undefined?
Exactly. But what? What do we say about this function? It was defined everywhere. Okay, so just check that. There's no one problem that I give you, because if I gave you a problem that had all the things you're supposed to be always checking, it would take you far too long to do that problem. Okay. All right. I did write one. I thought about giving it as an extra credit project for students. It's pretty messy. All right, what do we do next? What am I doing here? Zach? Jack.
Test
Sorry.
points.
Test points. Okay, so let's pick -3, -1.5, and 0. We're going to plug them into the first derivative. And we'll plug them into the second derivative. Okay. Folks, at this point, you should be doing that part on your own. Okay. So Max, did we find anything interesting on this function?
There's a local minimum between -1.5 and 0.
Specifically, where is it?
At -1.
Yeah, so we've got a local min at x equals -1. Great. And is there anything else of interest on this function? Please say, Thomas, anything interesting?
There's an inflection point
There's an inflection point where?
at -2.
At x equals -2. Okay, folks, I need a hand here. With the calculator, if you would go ahead and evaluate f of -1 and give me a decimal approximation, and evaluate -2 and give me a decimal approximation. I forgot to compute these beforehand.
-0.3678.
Okay, so we'll call it -0.37. We'll just go to 2 decimal places, and then if you do -2,
negative 0.2706. 7.
Negative 0.28, two
Yeah.
decimal places. Okay. All right, folks, what I'd like you to do now is graph this function. You put the rest of the pieces together. You've got. All right, so let's see here. I think we had 0, 0 was an x-intercept. It was also a y-intercept. Then I think we said that y equals 0 was a horizontal asymptote. And that was specifically as we were going to the left. We did say as we go far to the right, our y values get arbitrarily large, so I could go ahead and put that value, that arrow there. Okay. Then we found at the ordered pair -1, -0.37. So that's 1, that's 0.5. We had a local min. And at -2, -0.27. Negative 2.8, we have an inflection point. Okay. So we connect the dots. Now, we're coming from this way. Am I coming from way up above? Coming from way down below? No, I'm coming from this horizontal asymptote at y equals 0. Okay. Can't be above it. So got to be below it. I'm coming in like this. Till I get to there. I'm approaching the inflection point, decreasing in a concave down fashion. After I leave the inflection point, I continue decreasing, but now in a concave up fashion until I arrive at x equals -1, where I've got a local minimum. Then I continue in concave up, but now I'm increasing, heading off, taking off towards positive infinity. There's the graph of that function. Yeah, Thomas.
So if we went above, we would have a local, we would be creating a local base.
Yeah. Yes. There's a couple of reasons. One, so if I believe if I was going up, then I'd have to kind of. Did I say that? I'd either be exactly on the line, which I'm not, or I'd have to then be kind of moving upwards, which would then give me another local max. But I have no local maxes. Okay? And then, as Jack said, if I were above it, I'd have to cross the line y equals 0. But that I checked for that when I looked for all the x-intercepts, and that would create another x-intercept that I didn't initially have. And here's another thing you can do. When we said this limit right here came out to be 0, this is because as e approaches negative infinity, e to the x approaches negative infinity, that approaches 0, right? But how does it approach 0? It approaches 0 from below, because the output values, even though they're getting closer and closer to 0, are always negative. So that's another way of seeing that I would have been below that horizontal asymptote. So the limit was 0, but specifically we're approaching 0 from below because our output values were always negative. So that's another way to see it. Great question. Okay, folks. These problems take a long time. Okay? I need you to put some work into these. Okay? All right. I want to talk about, let me stop this. First thing we need to do is identify the domain of the function, right? What's the domain of this function?
Negative infinity to -1, and then -1 to infinity.
So you might think we need to exclude something in the denominator because we're doing division, right? But let's see, what's this expression always in the denominator here?
Positive.
It's always positive, right? Is there any way the denominator could ever be 0? No. Okay. So what is the domain of this function? All real numbers is what we can plug into it. Okay. So now let's go ahead and find the zeros of this function. How do we find the zeros? Well, we set the function equal to 0, right? When does that happen? Well, let's see. That happens when this fraction equals 0. There's many ways to sort of find your way through to the answer here. I like to always argue fractions this way. When is a fraction 0? When the numerator is 0, right? So that happens when x cubed equals 0. Great. That happens when x equals 0. Okay. So we've got it. X equals 0 is a 0. The next thing we do is we go to find the y-intercept, but again, in this case, it's not very exciting because the y-intercept is 0, 0. We know that because 0 is also a 0, therefore the y-intercept is 0, 0. Okay. Folks, I hope you're keeping track of the difference between x-intercepts and y-intercepts. I know that can be a little frustrating that all these answers come out to be 0, but if not, then it makes the derivatives in some of these problems much more complicated, so that's why this often happens. But please don't forget your basic algebra techniques of finding x and y intercepts. All right, now what do we want to do? Again, yeah, because on a test, I'm not gonna guide you through it, right? My math lab often baby steps you through problems, right? It says, well, you tell me what the 0 is, you tell me what the y-intercept is, which is great, but I'm not going to baby step you through it on the test. This is how your questions will look on the test. Here's a function, graph it. Yeah, so let's look for the vertical asymptotes and holes first, right? Vertical asymptotes and holes. Can a function have both a vertical asymptote and a hole at the same location?
Yes.
Who watched the video? Okay. I posted a video on D2L. Really interesting video of a function that had a vertical asymptote and a hole at 0. Pretty interesting. We hadn't encountered that before. So I do recommend that you watch that video. Okay? Right? Oof. Boy, I did something to kill the mood in here the other day. I haven't come back yet. I don't know what I did. Interesting dynamics. Okay, so do go watch the video. In this case, we have no vertical asymptotes or holes. How come?
There's no restrictions in the domain.
Yeah, I agree with Freddie. Freddie says, hey, the domain's all real numbers, right? So you can only have vertical asymptotes and holes by looking at exclusion in the domain. And we don't have any. So there are no vertical asymptotes or holes. Okay? All right, let's look at the horizontal asymptotes / long-term behavior. This is why I'm doing this example. This is long-term behavior. Okay. If you remember from college algebra techniques, there are no vertical there are no horizontal asymptotes to this function. Okay. And in fact, if we looked at the limit as x approaches infinity of our function is x cubed over x squared plus 1. If we look at that limit, okay, you now have a number of tools for evaluating this limit, right? In chapter 2, we said multiply by 1 over x raised to the highest exponent seen in the denominator. I'm going to do that technique just to practice, but what else could you use on this?
L'Hopital's rule.
You could use the L'Hopital's rule, which would be a fast way to, well, you'd have to do the L'Hopital's rule twice, I think. Once, twice. Yeah, you have to do it twice to get there. But let's go ahead and use the trick that we did in chapter 2. So I'm going to multiply by 1 over x squared divided by 1 over x squared. Oops. So when things clear, we've got the limit as x approaches infinity of x over 1 plus 1 over x squared. And we get a limit of what? Infinity, right? Because the numerator becomes arbitrarily large. This term's approaching 1, this term's approaching 0, so we've got an arbitrarily large number divided by 1, so arbitrarily large. Okay. I do think that L'Hopital's rule gives a better way of explaining that, because you apply L'Hopital's rule twice and you just end up with x over 1, well, you'd end up with 3x over 2 is 3 halves, so 3x over 2. But anyway, you still get a limit of infinity. Okay. All right, but that's not what I wanted to say. And likewise, if we looked at the limit as x approaches negative infinity of f of x, I'm not going to do the work. You would find out that it's negative infinity. Okay, folks, when I say I'm not doing the work, it's not because it's not important to show. It's just that in the interest of saving time, I'm not going to write it out. You should do that, though, to make sure you can see that the limit's negative infinity. Okay. Now what I want to look at, the reason why I wanted to do this function is this function, though, has an oblique asymptote. Okay? I don't feel like it's essential that you show the long-term behavior in all cases. However, if you have a rational function like this one, and the degree of the numerator is 1 more than the degree of the denominator, then you will have an oblique asymptote. And I want to go ahead and explore this because you had some of these tools in college algebra, but we weren't quite sure exactly what was happening, and so let's actually look at it now that we've got our limit tools. So I'm going to take the function x cubed over x squared plus 1, and I think of this as an improper fraction. Remember in grade school we said an improper fraction was where the numerator was bigger than the denominator, right? So for example, 3/2, that's an improper fraction. Okay? This is an improper fraction in the sense that the degree of the polynomial in the numerator is higher than the degree of the polynomial in the denominator. Okay? So I would like to go ahead and reduce this fraction down. Okay? And by the way, just as a reminder, if I had, say, the fraction 7/2, I would divide 2 into 7 3 times, and then I'd have plus a 1/2, right? So in old school division, you take 7 divided by 2, that goes in 3, that gives you 6, and you got a remainder of 1. Well, you could write that then as 3 plus the remainder over the divisor. Okay, that's something we haven't really thought about in a number of years, probably, which is okay. All right, so I'm going to do the equivalent of that with this improper fraction here. I'm going to do long division, it's called. So I'm going to take x cubed, and I'll go ahead and write plus 0x squared plus 0x plus 0, and I'm going to long divide it by x squared plus 1. You guys remember long division? If you've forgotten long division, that is okay for the time being. So how do we play the game of long division? It works like this. So if you don't remember this, pay attention here. Yeah, Will. Yeah, so the way we play the game of long division is this. We say, what do we need to multiply x squared by to make it look like x cubed? And the answer is x. And now I actually do that multiplication. So that gives me x times x squared is x cubed plus x. And I should line things up by their appropriate column. Plus x. Okay. This one isn't too exciting as far as doing long division. If you want a review of long division, I can give you some better examples another time. But notice now that when I subtract this down, I end up with a minus x here. What do we know about the degree of this compared to the degree of this? This has a first degree, this has a second degree, so this now has a smaller degree than what I started with, and so that's equivalent to having a remainder term that it doesn't go into anymore. Okay? So that means I could rewrite this as plus the remainder over the divisor, just like I did in that fraction just a moment ago. Okay? So that means that our original function could be rewritten as x plus x over x squared plus 1. Whenever you can do that for these polynomial functions, it will be the equation of the oblique asymptote. Sometimes it's called a slant asymptote.
Isn't the remainder is negative x?
Negative x. I apologize. Yes, that should be a negative there. Thank you. Good catch, Freddie, Angel. Oh, so I better put it up here too, huh? Holy cow. So that means if I now look at the limit, if we now look at the limit as x approaches infinity of our function, x cubed over x squared plus 1, that's going to equal the limit as x approaches infinity of x plus negative x over x squared plus 1, which is equal to the limit as x approaches infinity of x plus the limit as x approaches infinity of negative x over x squared plus 1. I'm going to leave the first limit here unevaluated. So I did the long division. I've distributed the limit to both terms. I'm going to leave the first one unevaluated. What happens to the second limit? What happens to this limit right here? It goes to 0. So we see that as x gets large, this function approaches the line y equals x. Okay? As x goes to infinity, the function approaches x. That's the line y equals x. Okay? So that means that on my graph here, let's see, there's 2, 2, there's minus 2, 2. So on my graph here, I'm going to have an oblique asymptote. What is the equation of this oblique asymptote?
Y equal X.
It's the line y equals x. And what I'm saying is as we approach infinity, as the x values get large, our y values get closer and closer to this dotted green line. Yeah, Will.
Will any equation or function where the degree of the numerator is exactly 1 greater than the degree of the denominator, will that always have an oblique asymptote?
Yes, if it's a rational function, yes. And in fact, we're not going to get into it, but if it's a rational function and the degree is higher by 2, it will have a quadratic asymptote.
So when it's always 1 plus, it's always y equals x?
No, that's a great question. So that was unique to this particular problem. So insert blank. So if I gave you this function right here, f of x is equal to 3x to the 4th power minus 7x squared all over x cubed. In fact, let's make this a 6x to the 4th over 2x cubed plus 1. Okay. If I do the long division on this, we'll take 2x cubed plus 1. We're going to long divide it into 6x to the 4th plus 0x cubed minus 7x squared plus 0x plus 0. Here I say, what do I need to multiply x by, or this first term by, to make it look like 6x to the 4th? And the answer is 3x. So we get 6x to the 4th plus 3x. We subtract down. In fact, let me make this actually, I'm going to change this once more. Let me make this plus 4x squared. So when I do this, we have 6x to the 4th plus 12x cubed. I then subtract this down. I get minus 12x cubed. I could also bring down this minus 7x squared, etc. So then I say, what do I need to multiply x by? Or sorry, what do I need to multiply this first term by to make it look like minus 12x cubed? And negative 6 is our answer, so we get minus 12x cubed. That gives me minus 24x squared. I change the sign, add down. I get 0, that's plus 24, so plus 17x squared. Notice now, at this point, the degree of the remainder is less than my starting degree. So that means we could rewrite this as, this function as 3x minus 6 plus the remainder, which is 17x squared, all over the divisor, which is 2x cubed plus 4x squared. And I changed that.
That's a quadratic equation.
No, No, I don't think so.
It's linear.
So this still has an oblique asymptote, but now it's not the oblique line y equals x. The oblique asymptote is the line y equals 3x minus 6. Okay. Still, as x goes to infinity, this term, so as x goes to infinity, the function approaches this line because this remainder term goes to 0. So the larger x gets on this function, the closer the function gets to just this line because this remainder term is going to 0. Yeah. So anyway, oops. We've got this horizontal asymptote at y equals x. Oops. So let's go ahead and do some more work with this. Okay. So we found horizontal and oblique asymptotes in behavior. We did vertical asymptotes, domain, zeros, y-intercept. So what remains to be done is our calculus chart. Okay. Well, we see from what I gave you that for the critical numbers we have no critical numbers of f. If you look at the first derivative, I've already given it to you in factored form. It is never 0 and it's never undefined. Right? Okay. But if we look at the critical numbers of f prime, that is, if we ask ourselves, where is the second derivative 0 or undefined, we have critical numbers at x equals 0 and x equals, is it plus or minus the square root of 3? Is that right? Yeah. Right. So when is the second derivative 0? Oh, I'm sorry, I made a mistake, folks. I'm jumping back and forth. We do have critical numbers to f, right? We have 1, x equals 0, f, and the critical numbers of f prime are 0 and plus or minus the square root of 3. Okay. We okay with that? I'm talking fast. Folks, here's our first derivative, here's our second derivative. Where's the first derivative 0 or undefined? At 0, it's 0, but it's defined everywhere else. Where is the second derivative 0 or undefined? It's 0 at 0 and plus or minus the square root of 3. Okay, so those are our critical numbers. So we build a number line. On our number line, we will put what? All of our critical numbers plus any places where the function was undefined. Okay, so we've got minus the square root of 3, 0, square root of 3. So we need some test points here. Let's take negative 2. Let's take negative 1, 1, and 2 as our test points. We'll plug them into the first derivative. Folks, I'm assuming at this point you've basically done a lot of these. So if you haven't, I'm going too fast for you. Okay? We're plugging the test points into the first derivative. So here's our first derivative. We're going to plug in, well, let's notice that the first derivative is always positive unless I plug in a 0. So it doesn't matter. All of these values when I plug into the first derivative are going to be positive. So we're increasing, 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 increasing. That makes sense. That makes sense. Okay. Let's double check that. Okay. And then let's go ahead and plug in those values into our second derivative. Okay. Well, when I plug in a 1, this factor is negative, this factor is negative. So I've got when I plug in negative 1, this factor is negative, this factor is positive. So the second derivative is negative at negative 1. Oops, I should have done negative 2 first, sorry. So we're down. If we plug in negative 2, that's positive, so everything's positive. So we're concave up. Okay. If I plug in 1, that's negative, so we're positive, so we're concave up. Folks, I'm going fast. I am plugging things into these charts, which you've been doing over and over again. So don't try to follow me. Just plug these numbers into the charts yourself. Okay? And then we get concave down for 2. Okay. Everyone okay with that? Okay. Great. So now I think we're ready to graph this thing. Okay. So we take our graph. On our graph, we put all of our interesting points that we found so far. Oh, do we need to say anything? Yes. I think we do. Do we have anything interesting on this graph? I think we have an inflection point at negative square root of 3 and at the square root of 3, right? Do we have an inflection point at 0? Yes. Yes, we do. I'm sorry. It is defined at 0. I'm sorry. You guys are exactly right. I'm wrong. And 0. Thank you. Okay. So let's put up all of our interesting points. Okay. So we had a 0 at x equals 0. We had a y-intercept at x equals 0. We've got an inflection point at the ordered pair 0, 0, right? So all that's happening at 0. If I plug in square root of 3 into the function, oops, I should have said f of square root of 3. Sorry about that. If I plug in square root of 3 into the function, I get approximately 1.3 out. Okay. So let's see here. If I plug in the square root of 3, which is a number a little bit bigger than between 1 and 2, I get out 1.3. Actually, let's see. I need help here, folks. What is the square root of 3 as a decimal? Sorry about that. I should have given you a decimal approximation of that also. 1.73. So I'm at 1.73 and I go up to about 1.3, so I'm below the line y equals x. Okay. And likewise then, if I plug in minus the square root of 3, because this is an odd function, and if you don't believe me, you just plug in the points. But this is an odd function, so if I plug in minus the square root of 3, I'll get out the opposite sign value, negative 1.3. So if I go out to about negative 1.7 and go down to negative 1.3, I'm about right here. And now I think we're ready to sketch this graph. Okay, this graph is always increasing. We are concave up, increasing in a concave up manner prior to getting to the square root of 3. Let's see. So we're increasing in a concave, oof, can't do that to save my life. Increasing in a concave up manner. Then we're continue increasing in a concave down manner. At 0, we again have inflection points, so we change from concave down to concave up. And then at 1.7, the square root of 3, we change from concave up to concave down. And there's the graph of that function. Folks, it would be nice to exaggerate that a little bit more. Okay. So I might, let me do that. I'm going to exaggerate that slightly. So let's move this point. I'm going to move these points out just a little bit to exaggerate that. You don't have to do this, but I'm just moving these out to exaggerate them. 7, 3. So we're increasing in a concave up manner, increasing in a concave down manner, increasing in a concave up manner, increasing in a concave down manner. And there's the graph of that function. Okay. Folks, the reason why I'm kind of throwing some of these examples out at you is just to kind of keep you from getting too complacent about these. Okay? Folks, in my opinion, this is the hardest section of this course. Okay? It requires the most work. Okay? In my opinion, too, it is also the easiest MyMathLab in this class because all of the answers are multiple choice. Because MyMathLab can't actually ask you to graph this by hand. And so students go through this section, and they say, oh, I got 100% on that homework. It took me 5 minutes. I must really know how to graph these functions. Okay? Please, 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 these examples that I'm doing in class are ones that I want you to rework a few more times. Additionally, I put up the graph of e to the 1 over x. Please, please, please look at that graph. Okay, so there's a video of that online. Okay, so anyway. Okay, folks, I want to go ahead and pick up on a graph that we haven't gotten to. This is listed in your notes in section 4.3, but it fits under this section of curve sketching, so we're going to take a look at it. We've got the function f of x is equal to 1 over x. And let's just run through our techniques. So the first thing we said is we want to identify the domain of this function. So where is this function defined? Well, we've got the exponential function, which is defined for all numbers, but then we've also got division introduced there. So we've got to make sure that we're not dividing by 0. So the domain of this function then would be all real numbers except for 0. Set of x such that x can be any real number except that x cannot equal 0. Or if you like, in interval notation, it would be from minus infinity to 0, union with 0 to infinity. So the next thing is we want to look to see if there are any x-intercepts to this graph. So let's go ahead and try to find any zeros. So to do that, we would set f of x equal to 0. If I set e to the 1 over x equal to 0, that's actually kind of a hard question to answer because I don't know what the graph of this function looks like, and I don't have really any algebraic means to try to solve for x. So we did this substitution quite a while ago. It was way back in chapter 2, where we can maybe put this in terms of a different variable. Let's call it u in this case. So let's let u equal 1 over x. If we do that, then we get when is e to the u equals 0. And this allows us to fall back on our knowledge of the exponential function's graph. So if this is u and this is e to the u, okay, when does this function touch across the x-axis? Well, it doesn't. So there's no solution to this, so then that means that there's no solution to this either. So because there's no solution, we know that there are no x-intercepts. So this graph, whatever it is never going to cross the x-axis. Okay. Well, the next thing we typically try to find is we try to find the y-intercepts if there are any. Well, to find the y-intercepts, we input the value 0 into the function. But we already said, go back and look at the domain, that we want all numbers, or the domain was all numbers except for 0, so that means f of 0 is undefined. So this is kind of interesting. This graph has no x-intercepts, no y-intercepts. The next thing we want to do is we want to explore the behavior near the exclusions in the domain. So let's look for vertical asymptotes / holes. Okay. And this is actually the reason why I want to do this example, because something really interesting is happening at 0 that we haven't encountered before. Okay. So to look for vertical asymptotes and holes, we're going to look at the limit as we approach the problematic areas in the domain. So let's look at the limit as x approaches 0 of e to the 1 over x. Well, this is a limit that's complicated enough. I probably ought to pick a direction of approach. So let's approach it from the right first. And let's see what we can do. Actually, I want to, doesn't matter, but let's start from the left. It's a little more interesting from the left. So this actual limit, we did it way back in section I think it was 2.4 or 2.5. And if you remember what we did then is we did a similar substitution to what I did just above. So I want to go ahead and replace 1 over x with u. But notice that my limiting variable is in terms of x. I now need to put it in terms of u. So let's see what we can do here. So our substitution is we let u equal 1 over x. So what do we see? Well, as x approaches 0 from the left, what is u doing? Well, u is approaching what? Well, let's say this, u equals 1 over x, and so is approaching, let's see here, we've got 1 divided by an arbitrarily small but negative number. 1 over a small negative is approaching negative infinity. Okay, so pay attention to what I did here. We started off with the limiting variable being x was approaching 0 from the left for this function here, 1 over x. But we went ahead and did a u substitution on that, and because of that I had to also adjust the limiting variable. So now we can answer this question based on our knowledge of e to the u, which looks like this. So instead of saying what happens as x approaches 0 from the left, we can say what happens in this graph as u approaches negative infinity. So as u is approaching negative infinity, our y values are becoming arbitrarily close to 0. So we get that this limit comes out to be 0. Okay. That was just when we chose to approach 0 from the left. What happens if we approach it from the right? So if we look at the limit as x approaches 0 from the right of e to the 1 over x, we're again going to do the substitution. We'll approach, we'll look at the function e to the u, but now what happens to our limiting variable? So as x is approaching 0 from the left, u, which equals 1 over x, is approaching what number? Well, let's see here. We've got 1 divided by, oops, I picked the wrong value. There should be a plus sign. So we've got 1 divided by a very, very small but positive number. That's approaching infinity. So this would be the limit as u approaches infinity. Okay. So this, again, this is a substitution technique. This is a difficult question to answer. We do a u substitution, and then it allows us to look at the graph of e to the u, which we know all about. So what do we see? Well, we see that as u approaches infinity, our y values are becoming arbitrarily large, and we get that this limit is infinity. Okay. So let's summarize this, because I think this is really interesting. We said the limit as x approaches 0 from the left of e to the 1 over x is equal to 0, and the limit as x approaches 0 from the right of e to the 1 over x is equal to infinity. So this tells us that we have a hole at x equals 0, and this tells us that we have a vertical asymptote at x equals 0, and this is probably the first graph that we've seen that has both a vertical asymptote and a hole at the same point. Okay, so the next thing I want to look at is the long-term behavior of the graph. Okay, so we've answered the question, are there any vertical asymptotes and holes, and we found yes, both at 0. So now we want to look at horizontal asymptotes or the end behavior. So what do we want to do here? Well, let's look at the limit as x approaches infinity of e to the 1 over x. Well, again, we'll play that game one more time with the substitution. So we've got the limit as something, as u approaches something, but this will be of e to the u. So now, as x is approaching infinity, u, which is equal to 1 over x, what's it doing? Well, the denominator is getting arbitrarily large. 1 divided by a large number is approaching 0. So here we have u is approaching 0. Specifically, I guess I should assign a direction here. U is approaching 0 from the right. So if we look at the graph of e to the u, what happens is we approach 0 from the right. Well, actually, the direction of approach doesn't matter. But as we approach 0 from the right, the y values are approaching 1. So this limit comes out to be 1. Okay. I won't work through all the steps, but similarly, as x approaches negative infinity of e to the 1 over x, we get 1 as well. So in this case, we would have the same graph. We'd be approaching this way. We also get to 1. Okay, so that gives us the end behavior. We know that we're going to have horizontal asymptotes at y equals 1, and that works in either direction. Okay, so now let's go ahead and look at some calculus to explore where it's increasing, decreasing, concave up, concave down, and identify any local maxes, mins, or inflection points. So let's take the first derivative of this. So we had f of x is equal to e to the 1 over x. So if we take the first derivative, we get, well, the derivative of e to an expression would be e to that expression, but there's a chain rule there, so we need to multiply by the derivative of 1 over x. Notice that there are no critical numbers to this. Why not? Well, critical numbers are where the function is, where the derivative is either undefined or equal to 0. Well, this derivative is undefined if I plug in a 0 for x, but we'd already excluded that from the domain of the function. And this derivative never equals 0 because that would happen if the numerator is 0, but we've already said that the numerator of that expression can never be 0. So we have no critical numbers in the first derivative. By the way, that means we will have no local maxes or local mins. Now let's look at the second derivative. So to do this, we're going to have to do the quotient rule. So let's go back to this formulation of it. So taking the quotient rule on the first derivative, we've got the bottom times the derivative of the top minus 1 over x. So the derivative of minus e to the 1 over x is minus e to the 1 over x times minus 1 over x squared. So that was the derivative of the, that was the bottom times the derivative of the top minus the top function minus the top function, which was minus e to the 1 over x times the derivative of the bottom, which is 2x, all over the bottom function, x squared. This looks like a mess, but it actually cleans up pretty nicely. We end up with e to the 1 over x plus 2x e to the 1 over x all over x to the 4th, or we could put that into factored form as e to the 1 over x times 1 plus 2x. So in this case, we've got critical numbers. The first derivative at x is equal to minus 1/2. Notice that even though this is still undefined at 0, neither was the original function, so 0 is not a critical number. And the numerator is only 0 if x is negative 1/2. Okay, so now we'll go ahead and build a number line. And on that number line, we'll put all of the critical numbers we found, in this case just at minus 1/2, plus any exclusions in the domain, which is 0. So now we pick some test points. Let's pick -1, -1/4, and 1. And we'll plug those into both the first and second derivative. So plugging those into the first derivative, we get f prime of the test point. Okay, so if you go all the way back to where we calculated the first derivative, which is way up here, if I plug in -1, well, this factor, this factor is negative, and this factor is positive, and this factor is positive. So the only thing dictating the sign on the first derivative is that negative sign. This is decreasing. Likewise, if I plug in -1/4 or 1, we get negative output values. So it's decreasing. Let's plug in these values into the second derivative. So if I plug these values in the second derivative, we're looking at this expression here. And if I plug in -1, the output is negative, so we get that the function's concave down at that point. If we plug in -1/4 into here, we get a positive value, so we're concave up. Likewise, if we plug in 1, we're concave up. So if we look at this chart, what do we conclude? Well, we can see that there are no local maxes or mins. We can see that there, in fact, then there would be no global maxes or mins, because we have no endpoints to check. And finally, we see that at x equals, -1/2, the graph changed from concave down to concave up. Since -1/2 was in the domain, that means we've got an inflection point there. Okay, so let's go ahead and put all that information together, and we'll build the graph. Okay. So let's see here. We have no zeros to put on here, no y-intercepts. We said that we had a horizontal asymptote at y equals 1. We said that we have an inflection point at -1/2. By the way, if you plug -1/2 into the original function, f of -1/2 is approximately 0.14. So if we plug that into the original function, we've got an inflection point right about here. Okay. We have no local maximums to put on there. We do have a hole. We have a hole here at 0, and that applies as we come from the left. And we had a vertical asymptote at 0 as well. So let's see if we can put this all together. Well, going back to our chart, we see that we're going to start out decreasing in a concave down manner. So if we come in here decreasing in a concave down manner, that inflection point, we get that. At -1/2, we have the inflection point, so we change from concave down to concave up, but continue decreasing, and we approach the hole that was at 0. After we step over this vertical asymptote, we are then decreasing in a concave up manner. Oops, quite right. We are decreasing in a concave up manner towards our horizontal asymptote at y equals 1. I think that's all I have to say about this, except this was the interesting graph where, notice what's happening at 0, we had both a hole and a vertical asymptote. If you have any questions on that, let me know. Okay, folks, so I want to graph one more of these. This is number 7 in the curve sketching section, section 4.4. And we're looking at the graph of this function right here. There'll be some curious points to this. So, running through our steps, the first thing we want to identify is the domain. And what's the domain of this function? It goes from -infinity to 0, union with 0 to infinity. Then the x squared factor is defined for all real numbers. The natural log expression is only defined for positive values. Well, x squared is certainly positive for everything except for x equals 0. So this is defined for all real numbers except for when x equals 0. The next thing we want to identify are the zeros of this function. So how do we find the zeros of a function? Well, we set the function equal to 0. That happens when x squared times the natural log of x squared equals 0. That happens when either of its two factors are 0. So that happens when x squared equals 0 or when the natural log of x squared equals 0 by the zero product property. Okay, well this happens when x equals 0, but what? Before we call that a 0 of the function, we initially said the domain was everything except for 0. So even though that's a true statement, that if we plug in 0 for x, well, it's actually not even a true statement, because it wasn't in the domain of the original equation, so we have to throw it out. Okay, but looking at the second factor, when is the natural log of x squared equal to 0? Well, it's the same time when e to the 0 is equal to x squared. So what did I do there? There's two ways of thinking about that. One is that I raised both sides to the power of e, but the better way to think about it, I think, is I wrote the logarithmic statement as its equivalent exponential statement. Well, what is e to the 0? It's 1. And so if we solve for x, we get plus or minus square root of 1, or we get x equals plus or minus 1. So the zeros are the x-intercepts then are at -1, 0 and at 1, 0. Those are the zeros of this function. Okay. Now let's go looking for a y-intercept if we can. Well, how do you find a y-intercept? Well, normally what you would do is you take your function, and if you're looking for the y-intercept, you're going to input a 0 value for x. But this is undefined in this case. Again, we identified the domain to begin with, and we said we could not plug in the number 0. Okay, so now we want to look for vertical asymptotes / holes. How do we find vertical asymptotes and holes? Well, we go through and we explore the boundaries of the domain. Well, this function was undefined at x equals 0, so we should explore the limit there. Let's look at the limit as x approaches 0 of x squared natural log of x squared. Now, normally when I'm looking at a limit approaching an exclusion in the domain, I might need to pick a direction of approach. But notice that both these quantities here, for the first factor and for the argument of the second factor, are being squared. So the direction of approach doesn't matter in this case. So we can just say as x approaches 0. Okay, well, let's identify this structure of this problem. The first factor is tending towards 0, but the second factor is tending towards negative infinity. So this is an indeterminate product, and we can't determine what that will be ahead of time. So we need to apply, well, we would like to apply L'Hopital's rule. We can't apply it just yet. Why not? Well, because L'Hopital's rule doesn't work for indeterminate products. It only works for the two specific indeterminate quotients that we mentioned. So what could I do? Well, the best choice is to take this first factor down below the line and invert it. Okay? I could have brought the natural log of x squared below the line and inverted it, but when I applied L'Hopital's rule, I would just end up with a mess. So in looking at these two, again, when you have an indeterminate product like this, you take one of the factors below the line and invert it. And the best choice is to take the x squared factor below the line. Okay, so this gives us the limit as x approaches 0. Now we're ready to apply L'Hopital's rule. How come? Because now this has indeterminate form minus infinity over infinity. So L'Hopital's rule now applies. We're applying it. Taking the derivative of the numerator, we get 1 over x squared times 2x, all divided by minus 2 over x cubed. Okay, so I took the derivative of the natural log of an expression, that's 1 over that expression, times the derivative of that expression. And the derivative of 1 over x cubed, we think of that as x to the minus 2 power. Then when we take its derivative, that's what we end up with. Okay, so we're getting closer to being able to evaluate this. Let's go ahead and clean it up a little bit. We get the limit as x approaches 0 of the numerator just cleans up to be 2 over x, all divided by minus 2 over x cubed. Inverting and multiplying then gives us x cubed, that should be x there. Inverting and multiplying the denominator to multiply these two fractions together gives us this expression, which is the limit as x approaches 0 of negative x squared, which is just equal to minus 0 squared, which is equal to 0. So what did we just determine? Way back up here, we were looking for our vertical asymptotes and holes. To determine where those are, we're going to explore the exclusions in the domain with limits. We took the limit of the exclusion in the domain and found out we got a value. And so what have we just shown? We have just shown that this graph has a hole at the, when x approaches 0, and the y-coordinate is also 0 there. So this is a hole at 0, 0. Okay, let's keep going. Now let's go ahead and find, I'll just keep going down. It's a little bit easier. Now let's go ahead and find our horizontal asymptotes. So to find the horizontal asymptote slash the end behavior of this function, we're going to look at the limit as x approaches both plus and minus infinity of this function of x squared, natural log of x squared. Normally I have to treat those two separate, but again, because both factors are being squared in terms of the x, both times x shows up, it's immediately being squared, the direction of approach doesn't matter. So approaching infinity or minus infinity is the same thing. That's kind of philosophical. All right, so notice that in either case, when I take either plus or minus infinity and plug it into the first factor, it gets squared, so it's an arbitrarily large positive number. And when I plug in plus or minus infinity into the second factor for x, it gets squared, so it's arbitrarily large positive. Then I take the natural log of an arbitrarily large positive, which is still arbitrarily large and positive. So this has the form, let's just say that this, not the indeterminate form. Notice I'm not writing IF, I'm just putting the form infinity times infinity, and there's no ambiguity there. That is infinity. Okay, so we found the horizontal asymptote slash end behavior. So at long last, we're starting to look at the derivatives because we want to identify where we're increasing, decreasing, spot any local maxes and mins. And we also want to identify where we're concave up, concave down, and spot any inflection points. So let's see here. Let's take f prime of x. So let's see, I'm going to recopy f of x just so I've got it ahead of me. Natural log of x squared. So we're going to have to do a product rule. We'll call this the first factor, this the second factor. So when we do the product rule, we get the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. Let's clean up this mess. We end up with 2x plus 2x natural log of x squared. Factoring out a 2x gives us 2x times 1 plus the natural log of x squared. I want to identify the critical numbers of f. Remember, the critical numbers of f are where the derivative of f is either undefined or 0 for interior points in the domain. Well, the first derivative of f is undefined when x is 0, but that x value is already excluded from the domain, so we're not going to pick that up as a critical number. Don't worry, we'll explore its the behavior there anyway. But then we could ask the question, when else could this be 0? Well, it would happen if 1 plus the natural log of x squared equals 0. So when does 1 plus the natural log of x squared equal 0? That happens when the natural log of x squared equals -1. Well, when would that happen? Well, let's see. I can't solve that in my head. Let's rewrite it as its equivalent exponential statement. So that happens when e to the -1 equals x squared. That is when x squared equals 1 over e. So that would happen when x equals plus or minus the square root of 1 over e. Or we could write plus or minus the square root of 1 over the square root of e. Either of these is acceptable. Okay. So those are our critical numbers of f. Now let's go ahead and look at the second derivative here. Dots out of there. So the second derivative, let's see here. I'm going to recopy the first derivative. We said it was 2x plus 2x ln of x squared. So now let's go ahead and find the second derivative. So the second derivative is differentiating termwise. There's the derivative of the first term. And then I'm again going to have to do this product rule. So let's see here. This would be the first times the derivative of the second, whoops daisy, times the derivative of the second, 1 over x squared times 2x, plus the second, natural log of x squared, times the derivative of the first. When we clean everything up, let's see here, we have this 2 plus, let's see here, that gives us 4x squared over x squared, so that's just plus 4, plus 2 natural log of x squared. So this simplifies to be 6 plus 2 ln of x squared. So where is this, so let's find the critical numbers now of f prime. Remember, the critical numbers of f prime will be where its derivative, the second derivative, is either undefined or where it has zeros. Well, its derivative is undefined at 0, but so is the derivative of f, so that's not going to be a critical number. But we could have the instance where 6 plus 2 times the natural log of x squared is equal to 0. That would happen when 2 times the natural log of x squared is equal to -6, or when the natural log of x squared is equal to -3. I can't solve that in my head, so let's go ahead and rewrite it as its equivalent exponential statement. So what's its exponential statement? We would say that e to the -3 is equal to x squared, or plus or minus the square root of 1 over e cubed is equal to x squared, equal to x, applying the square root method. Or what could we do? We could also say that x equals 1 over e to the 3/2, plus or minus. So might have been a little bit fast. Let's see here. The square root of 1 over e cubed is the same thing as the square root of 1 over the square root of e cubed. But that's the same thing as just 1 over e to the 3rd to the 1/2 power. Square rooting and fractional power 1/2 are equivalent, and we get 1 over e to the 3/2. So that's where I got that from. Okay. So we've got our critical numbers, and if you go way, way back up to my problem statement, way up here, you'll see that I went ahead and gave you decimal approximations of those critical numbers, because I don't know what those are off the top of my head, and that gives me a sense of where they'll fall on the number line. So I'm ready to now create my number line. So here we go. I'm going to put a number line up here, and what am I going to do? Well, I'm going to first put all the places where the original function is undefined, any exclusions in the domain of the original function. So I've got to put 0 up there. Then I'm going to put all the critical numbers of f. Well, f had critical numbers at 1 over the square root of e, I believe. Is that what we had? That should be a minus sign, but yeah. Minus 1 over the square root of e and 1 over the square root of e. So these were when f prime of x were equal to 0. When f prime of x was equal to 0, whereas this is where f is undefined. Then we also should put up where f prime has critical numbers, the potential locations for our inflection points, and those happen at 1 over e to the 2/3 minus, and at 1 over e to the 2/3. So we've got our number line, and this is kind of a messy one. That's why it was helpful to have decimal approximations of there. Remember, this is about -0.6. This is about -0.2. Was it what I said? I forget. -0.22. This was about 0.22, and this was about 0.6 or thereabouts. Okay, so I can now take test points on all sides of those. So let's go ahead and do that. Okay, so we could take, for instance, -1, -0.5, -0.1, 0.1, 0.5, and 1 as our test points. And then we can determine, well, we'll first determine the intervals for which we're increasing and decreasing. Okay. Now, folks, I'm going to cheat a little bit here. To be honest, evaluating these would take some time. If you plug -1, if we were to plug -1 into our first derivative, sorry, I'm probably giving you motion sickness here. Where is our first derivative? Here it is. If we were to plug -1 into our first derivative here, and then decide the sign, well, it would take us a little bit to figure this out, but it turns out that we would be decreasing. Okay, so I'll let you check that. And if we were to plug in -0.5, we would be increasing, and again increasing, and then decreasing, decreasing, increasing. So you can check me on those. We've done this half dozen times now. We've plugged these test points into the first derivative, and we've looked at the sign. Okay, again, doing that takes a little bit of time. I went ahead and computed those beforehand. So then we could look at f double prime of our test point. What are we deciding on these intervals? We're deciding the concavity. So let's see here. We go up to our second derivative. Usually you want to do this in factored form, although you don't have to. I guess I never factored the second derivative. But if we plug -1 into the second derivative, we can determine the concavity. Well, that would take a little bit of checking, but if we do so, that would take a little bit of checking, but if we did so, we would find that we are concave up, and then concave down, because the sign there changes from positive to negative in that interval, and we would still be concave down, concave up, concave up. Okay. There is a little bit of a pattern here you might recognize. Our original function, I didn't say this, our original function was an even function. And so that means that its derivative will be an odd function, and the second derivative can be even, which is why you have the two patterns that you see in the intervals for increasing, decreasing, and concave up, concave down. Okay, so I think we're ready to graph this thing. All right, we'll go ahead and do this. Ooh, that's not going to give me enough room. All right, let's go ahead and graph this thing. So, and again, on an exam, I would give you a prefabricated axis, so you don't have to worry about scaling and whatnot. But let's see what we can do here. So, let's start putting in the interesting points. Well, we said that at -1 and again at 1, we had zeros to this function. So our function was 0 there. 0 there. we said we had no y-intercepts. Okay, there are no y-intercepts. And then we said we had no vertical asymptotes, but we did have a hole where? We said the location of our hole was at 0, 0. So we got a hole there. Then we said that our long-term behavior, as we went far to the right, we go up, and as we went far to the left, we go up. If you look at the long-term behavior statements. So our graph is looking sort of like this. Okay. Then we had 1 over the square root of e, which is about negative 0.66. So maybe I'll put it there, minus 1 over the square root of e. And we also had positive 1 over the square root of e. And if we evaluate those in the function, here I'm going to have to go up and see what we'd said. When we plug 1 over the square root of e into the function, we get about negative 0.37. Okay. So I'll put those way down here. We get, oops, blue. We get this point right here and this point right here. That's 1 over the square root of e, comma, and then I'll just put approximately negative 0.37 and 1 over the square root of e, minus 1 over the square root of e, comma, approximately negative 0.37. And folks, in the statement of the problem, I only told you this fact, but because this is an even function, then that fact must also be true. Okay, then we need to put up our 2 inflection points that we found. We found that we had one at 1 over e to the 3/2 and another one at minus 1 over e to the 3/2. And we could place that inflection point here and that inflection point here. And let's see here. What did we say the approximate values of those were? We said that f of the location of that is approximately negative 0.15. So this is about negative 0.15. Let's see, probably label this here. So this would be 1 over e to the 3/2, comma, approximately negative 0.15, and 1 over e to the 3/2, oops, that's minus, comma, negative 0.15. Ooh, it's got ugly. Okay, so we're ready to now we've got our points plotted, we're ready to put this all together using our increasing, decreasing / concavity chart. So before we get to this point of this, notice this is a local minimum here. Before we get to the point of that local minimum, we're going to be decreasing in a concave up manner. So before we get to right here, we're going to be decreasing in a concave up manner. So let's see here. Here we are decreasing in a concave up way. I'm going to erase that arrow now. Then, according to our chart, we've got a local minimum there because that was a critical number, right? That was a critical number, so that gave us a local minimum. Now we're going to be increasing in a concave up manner. So we sketched the curve. Now we're increasing in a concave up manner until we get to this inflection point. At the inflection point, let's see here. Here's the inflection point. We know it's an inflection point because that's where we changed from concave up to concave down, and it was a point defined on the original function. So we got an inflection point because we continue increasing, but now we do so in a concave down manner. So we continue increasing, but in a concave down manner. All right, that looks pretty ugly. I'm going to go ahead and fix that real quick. I might erase a little bit, but that's okay. So let's get that cleaned up just a little bit, increasing, great. And then we arrive at this hole. So notice I'm not putting a point in that hole. Make sure it doesn't look like there's a point there. I'm botching this up, but we'll survive. Okay, and then after I leave the hole, okay, and this is why I wanted to put 0 on here. Even though it's not a local max or local min or inflection point, anything like that, stuff still happens at that undefined point of the graph. So I did need to include that in my chart. And we notice that we begin, oops, where did it go? Okay, after we leave the hole, we will be decreasing in a concave down manner. So we're decreasing, but in a concave down manner until we get to this point of inflection, at which point we change our concavity. We will continue decreasing, but now in a concave up manner. We arrive at our local minimum right here, and we continue increasing in a concave up manner after we leave the minimum. And there we have the graph of this function with all of the interesting points labeled on it. That's good enough for sour apple.